Hi class. So this is an example that goes with lecture 34, which is our second lecture on pumps and turbines. These examples have to do with the net positive suction head and with putting pumps in serial or parallel. So let's go ahead and get started. We're going to start with the first example, which is an example about NPSH. So I'll put that under here, NPSH. And I'm looking at a pipeline system suppose I know what the operating point is going to be. So suppose that I've already solved for the operating point and I know that it's going to be 16.6 liters per minute and the head at operation is going to be about 6.5 meters. And I want to know if at this operating point will the system cavitate. So that's the question I want to ask. And I know the head at the inlet to the pump, so I know that the head is this function here, 13 meters minus B, which is 0.021 meters over liters per minute squared, times the flow rate squared. That's the inlet. And I know that the required NPSH from the manufacturer is 0.034 meters per liters per minute squared times Q squared. And I know the vapor pressure is 26.5 kilopascals. And so the question is, will the system cavitate? Well, the requirement that I have is I need to find where NPSH equals NPSH required. Okay, so what I need to do is, if I think about this, if I have NPSH here, which is a head, as a function of Q, I need to find where, if I have NPSH going like this, and I have NPSH required going like this, okay, I need to find where that point is, all right? And then I need to see where the operating point is, okay? If at the operating point, let me just make sure I have this right here. If the operating point is out here, okay, if this is the operating point right there, then NPSH required is bigger than NPSH, and I'm going to cavitate. Okay, if I have that guy. But if the operating point is over here, if that's my operating point, then my NPSH is greater than my NPSH required, and this is fine. Okay, this one won't cavitate. Okay, so that's what I'm asking. So remember that we need the NPSH, the net positive suction head, to be greater than the NPSH required in order to have no cavitation, in order to be able to operate the way we want. Okay, that's what we need to check. So what we need to figure out is our NPSH. We're given NPSH required right there. We need to figure out NPSH. So NPSH is equal to the inlet head minus PV over rho G. So the inlet head is A minus BQ squared, now minus vapor pressure over rho G. Okay, so I can put in numbers. 13 meters minus 0.021 meters per liters per minute squared multiplied by Q squared minus, and then the vapor pressure is 26.5 kilopascals. And assuming that this is water, I'm going to have, rho, it's going to be 10 to the 3 kilograms per meter cubed. And of course, gravity is 9.8 meters per second squared. All right, so you need to do a little bit of unit conversions to make that all work out. But this guy is just going to subtract from this constant bit, and it's going to give me 10.3 meters minus 0.021 meters over liter per minute squared, Q squared. Okay, so now I need to find that point where they're equal, so I need to set NPSH equal to the required NPSH. So I'm going to have 10.3 meters, I don't want a capital M, lowercase m, minus 0.021 meters over liter per minute squared is going to equal 0.03, oh, I forgot my q squared, 0.034 meters over liter per minute squared, q squared. Okay, and now I can add this piece over here and divide by that and take the square root. That's what I'm going to do. So I add to both sides and I get 10.3 meters is equal to the sum of those two guys, which is 0.055 q squared, which this has meters over liter per minute squared on that piece right there. And now I'm going to divide that on both sides, and I get q squared is equal to 10.3 divided by 0.055, and the meters will cancel, and I have liters per minute squared. And so now I can take the square root, and q is equal to, the square root of that is 13.7 liters per minute. Okay, so now let's look back up here, think about our picture, and think about, so this crossing point right here is going to be at 13.7 liters per minute. So where was our operating point? Our operating point is at 16.6 liters per minute. So it's out here. So this system will cavitate. So that's frowny face, okay? System will cavitate. Okay, so notice that the Q that we solve for, this is going to be the maximum flow rate. Okay, so if we have a Q that's higher than that one, then we're in trouble. Okay, if it's less, then we're fine. And that's because we need the NPSH to be greater than the NPSH required in the pump. Right? So that's the first example about NPSH. Let's turn and do a second example down here. So this will be example 2. I'm going to fix that little dot. Example 2. Okay, and example 2 is I'm going to do pumps in parallel. Okay, so assume I have 2 pumps. Suppose I have 2 pumps in parallel. So I've got this guy, and I've got another one down here. Okay, and they're hooked up, you know, suppose this is some tank system. All right, and suppose that my system demand, oh, I want to skip that first S. Suppose my system demand is given by some C plus D Q squared. Okay, and this is Q total, all right, the Q through the whole system. And suppose that I know these 2 pumps, I've got pump 1 and pump 2, so we'll call that pump 1, call that pump 2. Suppose that HP1, I know my pump performance curve for 1 is A1 minus B1 Q squared, okay, where Q is Q1 squared, and HP2 is A2 minus B2 Q2 squared, all right? And I want to find the operating point. Okay, so now the key to these problems, all right, are we need to remember the following. We need to remember that the system demand curve needs to equal the total pump performance, okay, curve. So that's the thing we need to remember on both serial and parallel. But then we need to remember the key idea in, the key principles. So what are the key principles? Okay, the key principles are, 1, that the flow rates in these cases sum. So Q total is going to equal Q1 plus Q2. And the other key principle is that the head has to be the same. So HP has to equal HP1 plus HP2. All right. So this is for parallel, remember. Okay, one for serial are opposite. So now how are we going to solve this guy in this case? So notice that I have the system demand curve is in terms of Q total, okay, but these are in terms of Q1 and Q2. So that makes my life a little difficult. And then I have these guys here, which are in terms of, I need my, this is wrong right here. This isn't the sum of these, pardon me. The pump, the head to each pump has to be equal in parallel. I don't know if I said that wrong or if I just wrote it wrong, but let me just restate the key principles to make sure. So the key principles are that in parallel, the flow rates sum, right? I have two different branches, so the flow rates are going to sum, right? And but the head has to be equal, okay? So I have to have the same head through that branch as through that branch, all right? So now how am I going to equate this here? How am I going to do that? Well, I need to find what HP is, all right, which I'm going to have to do, and I have to find what Q is. Well, let me invert this to find Q1 and Q2, and then I will sum them, and that will tell me what Q total is. So let me do that first. So I'm going to take HP1, and I'm going to invert it. Okay, so to do that, what I'm going to do is just solve for Q1. So I have HP1 minus A1 is equal to minus B1 Q1 squared. So I just moved A1 over. Now I'm going to divide by minus B1. So it's like the ugliest arrow ever. Okay, so I divide by that. Now I get A1 minus HP1 divided by B1 is equal to Q1 squared. So Q1 is equal to the positive root of A1 minus HP1 divided by B1. Okay, and I can do a similar thing for HP2. Can invert that one. Okay, and I'm going to have something very similar. It's the same algebra. So what I'm going to get there, so I'm going to just write same algebra. Okay, and that's going to give me that Q2 is equal to the root of A2 minus HP2 divided by B2. Okay, but I know that HP1 has to equal HP2, so that's just HP. So I can combine these and write that the total Q is equal to Q1 plus Q2, which is equal to the square root of A1 minus HP divided by B1 plus the square root of A2 minus HP divided by B2. And now I have something where I have Q total as a function of HP, all right? And I've got my system demand curve up here, which is also in terms of Q total. All right, well now I'm getting somewhere. So now I look here, and it would be nice if I could solve this and invert that guy back and get HP as a function of Q total. Okay, I would like to do that. Okay, but I don't know how to do that where I'm summing this root. But it turns out I don't have to, because if I can say Q total at HP is equal to Q total of H system, okay, that's going to tell me what my Q operating point is, and I can use that to find my H operating point too. So I can use this guy just as easily as I can use the other one. So that's what I'm going to do, is I'm going to invert my system demand curve. So I have H system now, and I'm going to invert that guy. Okay, so let me look up here. H system is C plus D Q total. So let me copy that down. H system is equal to C plus D Q total squared. All right, and now I just need to invert and solve for Q total. So I'm going to have H system minus C divided by D is equal to Q total squared. And so Q total as a function of H system is equal to the square root, the positive root of H sys minus C divided by d square root. Okay, so now to solve for the operating point, I set these two equal to each other. I set this guy and that guy equal to each other. And now I'm going to have to solve the problem of H system minus C divided by D is equal to the square root of A1 minus HP divided by B1 plus the square root of A2 minus HP divided by B2. Oops, that was a mess. B2. Okay, and you say, well, what is this? I have two of these guys, HSys and HP. But I said that HSys equals HP equals H operating point. Okay, so I just plug that in, and now I need to solve this equation for the operating point. So this one, again, this is hard to do by hand, but I can use Newton's method to solve that. Use the computer to solve this guy. So at the end of the day, I'm going to use a computer and I'm going to solve something like 0 equals minus the square root of H operating point minus C divided by D plus the square root of A1 minus H operating point divided by B1 plus the square root of A2 minus H operating point divided by B2. And I'm going to solve that, which is some function of H operating point to find the operating point. Once I have that, I can go back and plug it into one of my equations up here, like this one. Okay, and I can then, plug in after solve, okay, to get Q operating point. Right? So these parallel ones are a little tricky because you have to invert them. If I remember correctly, the serial ones are quite a bit easier because in that case you're summing these and these have to be equal. And it's a straightforward calculation where you just sum each of the heads. All right. So serial, serial is easier. Okay, that's why I did the hard one here. So in serial you have Q total is equal to Q1 is equal to Q2. But the HP total now has to be the sum. HP1 plus HP2. Right? So those are the two examples I wanted to give you. I hope this is helpful in getting your homework done. And we'll talk to you next time.